Good afternoon and welcome to Portal TV. I'm your host for the show, Tim O'Connor, and this is SyTech number 43. Berkeley Lab researchers fabricated the first fully 2D field-effect transistor from layers of molybdenum disulfide, hexagonal boron nitride, and graphene held together by van der Waals bonding. Wow! What does that all mean? Actually, some pretty cool and important stuff. This means that faster electronic device architectures are in the offing with the unveiling of the world's first fully two-dimensional field-effect transistor, or FET, by researchers with the Lawrence Berkeley National Laboratory, the Berkeley Lab. Unlike conventional FETs made from silicon, these 2D FETs suffer no performance drop-off under high voltages and provide high electron mobility even when scaled to a monolayer in thickness. How thick is a monolayer? A monolayer is a single, closely packed layer of atoms, molecules, or cells, depending on the application. In this instance, we are speaking of the atomic level. Al Javi, a faculty scientist in Berkeley Lab's Materials Sciences Division and a UC Berkeley professor of electrical engineering and computer science, led this research in which 2D heterostructures were fabricated from layers of a transition metal dicacogenide, hexagonal boron nitride, and graphene stacked via van der Waals interactions. Now, I've mentioned this twice. What is a van der Waals interaction? Van der Waals forces include attractions and repulsions between atoms, molecules, and surfaces, as well as other intermolecular forces. They differ from covalent and ionic bonding in that they are caused by correlations in the fluctuating polarizations of nearby particles, which is a consequence of quantum mechanics. English, Tim. English, you scream. I am speaking English. Read a book. Okay. Static electricity, the boon and bane of every child who is not an only child and loves to shock, torment, and electrocute said other siblings in the household on cool, dry days. The static charge, exhibit 1 of the crime, with either socks, hands, or other materials creates an imbalance of electrical charges within or on the surface of a material. Thus the result, exhibit 2 of the crime, is perpetuated upon an unsuspecting loved one. The problem with this is this force dissipates over time. A van der Waals interaction is a molecular bond. So whether with nanofibers or a graphene surface, with the van der Waals force created upon it is a force which is inherent in the property itself and will never dissipate over time. Javi says our work represents an important stepping stone towards the realization of a new class of electronic devices, in which interfaces based on van der Waals interactions rather than covalent bonding provide an unprecedented degree of control in material engineering and device exploration. The results demonstrate the promise of using an all-layered material system for future electronic applications. FETs, so called because electrical signals sent through one electrode creates an electrical current throughout the device, are one of the pillars of the electronics industry, ubiquitous to computers, cell phones, tablets, pads, and virtually every other widely used electronic device. All FETs are comprised of gate, source, and drain electrodes connected by a channel through which a charged character, either electrons or holes, flow. Mismatches between the crystal structure and atomic lattices of these individual components result in rough surfaces, often with dangling chemical bonds, which is an error in structure creation and computational chemistry that degrade charge carrier mobility, especially at high electrical fields. Now, this has always been a big problem in silicon creation. In constructing our 2D FETs so that each component is made from layered materials with van der Waals interfaces, we provide a unique device structure in which the thickness of each component is well defined without any surface roughness, those dangling bonds, not even at the atomic level, Javi says. The van der Waals bonding of the interfaces and the use of a multi-step transfer process present a platform for making complex devices based on crystalline layers without the constraints of lattice parameters that often limit the growth and performance of conventional heterojunction materials. Now you end up with an interface, basically all that is pristine. Javi and his team fabricated their 2D FETs using the transition metal dichalcogenide molybdenum disulfide as the electron-carrying channel, hexagonal boron nitride as the gate insulator, and graphene as the source, drain, and gate electrodes. All of these constituent materials are single crystals held together by van der Waals bonding. For the 2D FETs produced in this study, mechanical exfoliation was used to create the layered components. In the future, Javi and his team will look into growing these heterogeneous layers directly on a substrate. They will also look to scale down the thickness of individual components to a monolayer and the lengths of the channels to molecular scale dimensions. So, what does all this mean for the future? Very small, low heat, high powered digital tech is just the tip of the iceberg. Imagine the possibilities. That's all I have today for SyTech. Now on to gaming. I just can't wait. Be right back.